In this lecture, what we'd like to do is take the methods that we just learned in the last lecture and apply them to some of these sequences that we've seen above. So I've written down again some of the sequences we looked at before. They're in a different order, but we'll just play with them anyway. Here, let's say we have a sequence that starts with 0 and 1. So A0 is 0, A1 is 1. This is the one we mentioned when we first started looking at recursively defined sequences. And we have this recurrence relation. A sub n is 3 times a n minus 1 minus 2 times a n minus 2. That's valid for all n greater than or equal to 2. So again, 3 is 3 times 1 minus 2 times 0. The 7 is the 3 times 3 minus 2 times 1. The 15 is 3 times 7 minus 2 times 3, etc. Can we find a formula that will tell us exactly what the nth term is? Remember, this is the nth term. This is A0, A1. I'll just skip here. A2, 3, 4, 5, 6. This is A6, A7, A8. Just so you see how this sequence kind of progresses. And you might be able to guess a formula ahead of time. Let's see if your guess is correct, that a formula for these terms. Well, what is the characteristic equation? It's just going to be exactly r squared equals 3r minus 2, or r squared minus 3r plus 2 equals 0. We can factor that as r minus 2 times r minus 1 equals 0. So r has to be either 1 or 2. So our two solutions are alpha equals 1 and say beta equals 2. These are our solutions. And they're two distinct solutions. So we know that the general form of a sequence that satisfies our recurrence relation is that a sub n should be some constant a times 1 to the n plus some constant b times 2 to the n. Here's our alpha to the n and our beta to the n. What are a and b? Well, to find a and b, we have to solve the system where when n equals 0, we have a0, which is 0, equals a plus b. And when n equals 1, we'll have 1 equals a plus 2b. And this is, of course, a very easy system of two linear equations in two unknowns. So we solve this system, and you can probably do that in your head. What's a good way of doing it? We take the second equation minus the first equation, and we get 2b equals 1. So b, excuse me, b is equal to 1/2. And if b is 1/2, a has to equal, I'll say that's not b equals 1/2. Let me say that again. We take the second equation minus the first equation, we get b equals 1. And then because b is 1, a has to be equal to minus 1. There we go. And that tells us a sub n is precisely, I'm going to just rearrange these, b equals 1, so I'll have 2 to the n times 1, minus 1 times 1 to the n, which is just 1. And you'll notice that by solving the system of two linear equations in two unknowns, this definitely will work for the first two terms. You can check it, of course. 2 to the 0 minus 1 is 0. 2 to the 1 minus 1 is 1. And I claim this holds for all subsequent terms. It certainly is easy to check that it holds for, say, a6, which is 2 to the 6th minus 1. a8 is 2 to the 8th minus 1. And each time we'll get 1 less than a power of 2. So I have a formula for the nth term. As I said before, you could have probably guessed a formula and then just used induction to demonstrate that it's correct. But when we use this method, we know that this has to be the correct solution. Let's look at this second sequence here. A0 is 2, A1 is 1. And we use the recursion relation. A sub n is an minus 1. The previous term plus 6 times the term before that. 13 is 1 plus 6 times 2. 19 is 13 plus 6 times 1, etc. Is it easy to solve this recurrence relation? Well, the characteristic equation is just going to be r squared equals r plus 6, Or I can write r squared minus r minus 6 equals 0. I can factor that as r minus 3, r plus 2 equals 0. So I have two solutions to the characteristic equation. I can use alpha equals 3 and beta equals negative 2. What does that mean? That means our general solution to just the recurrence relation part is that a sub n will be a constant times alpha, that's 3 to the nth power, plus some other constant times beta, which is negative 2 to the nth power. And to get the a0 and a1 terms correct, we need to find the appropriate capital A and capital B. So we need, when n equals 0, we need 2 to be a plus b. And when n equals 1, we need 1 to be 3a minus 2b. So we need to solve this system of two equations and two unknowns. If I take this second equation and add to it twice the first equation, you'll see the b's will cancel. And when I do that, I'll get 5 equals 5a, or a equals 1. Once I know a equals 1, then b equals 1 as well from the first equation. So b equals 1, 2. And we get a sub n is exactly 3 to the n plus negative 2 to the n. And you can check that. 3 to the 0 plus negative 2 to the 0 is 2. 3 to the first power plus negative 2 to the first power really is 1. That means we've done things correctly, solving our system of two linear equations. When n equals 2, for example, we have 9 plus 4 gives us 13. When n equals 3, we get 27, but now we'll have minus 8, which is 19. When n equals 4, we'll get 81 plus 16, which is 97, etc. So it certainly seems to work here. And because we know that 3 and negative 2 are solutions to the characteristic equation, we know that this will satisfy the recurrence relation that we have, and it will be the correct formula. And you might have guessed, we can use the exact same techniques to get a formula for the Fibonacci sequence. The Fibonacci sequence, let me remind you, it starts with a 1 and a 1, and has the recurrence relation that for all n greater than or equal to 2, f sub n is f sub n minus 1 plus f sub n minus 2. So we go on to 2, 3, that's the 1 plus 2, and then you have the 2 plus 3 is 5, the 3 plus 5 is 8, 13, you should be comfortable with this sequence, 21, 34, etc. How can we get a formula that will tell us exactly what f sub n is without having to go through this process of building up the sequence all the way until we get there? Well, what's the characteristic equation? It's just going to be r squared equals r plus 1. Or we can write r squared minus r minus 1 equals 0. That doesn't factor nicely in nice integer rational ways, but we can use the quadratic formula. Which tells us our solutions are, if we think of this as our coefficient as our little a, our little b is negative 1, and our little c is negative 1 for the quadratic formula, we have minus b, which is 1, plus or minus square root of the b squared, which is 1, minus 4ac, which gives us a plus 4, all over 2a, which is 2. This is going to be 1 plus or minus root 5 over 2. In other ways, we can use alpha to be 1 plus root 5 over 2, and beta to be 1 minus root 5 over 2. We have the two distinct roots. Then we can say that the nth term, f sub n, will just be some constant times alpha, which is 1 plus root 5 over 2 to the n, plus a different constant, b times beta, which is 1 minus root 5 over 2 here to the nth power. How do we find a and b? We just look when n equals 0, we get a plus b here, and we need to get 1, so we solve the system where 1 equals a plus b. And when n equals 1, we get f1 equals 1, and that will be 1 plus root 5 over 2 times a plus 1 minus root 5 over 2 times b. And this is still just a system of two linear equations and two unknowns. The coefficients are messy, but that shouldn't worry you. As a fun exercise to make sure you're still good at manipulating things, I'll leave it to you guys to work out the details. I claim that in the end, we can solve this. As I said, we always will have unique solutions here because the coefficient matrix is non-singular. So the unique solution will be a is 1 over root 5 times 1 plus root 5 over 2. You can certainly write that in many different ways. And b will be minus 1 over root 5 times 1 minus root 5 over 2. And so if we just put in those a and b, we get a formula for the nth Fibonacci number, which I've written here. I'm not sure why that last stuff didn't disappear here. I think that's something weird going on. Just ignore the bottom there. We have f sub n. Oops. The nth Fibonacci number, f sub n, is just given by 1 over root 5. I've taken one of these 1 over root 5, 1 plus root 5 over 2, and multiplied it by the 1 plus root 5 over 2 to the nth to get this 1 plus root 5 over 2 to the n plus 1. And then here's the other term, minus b, which is 1 over root 5 times 1 minus root 5 over 2. I'm sorry, and minus that, times the 1 minus root 5 over 2 to the n. I've combined them into this beautiful formula for the nth Fibonacci number. And I say beautiful formula because, of course, you look at that and probably think that's some really horrible formula. But there are many interesting things about this formula. First of all, this number here, 1 plus root 5 over 2, is a very important number in mathematics. We often use the name phi for it. It's the golden ratio. And there are a lot of things we can talk about how important the golden ratio is. Let's start with what's strange about this formula other than just the messy form of it. Remember, f sub n is always an integer. It solves a counting problem, the counting problem with the rabbits. Also, it starts with f naught equals 1 and f1 equals 1, and after that, by the recurrence relation, we just keep getting integer values at each stage. You have to get an integer for any value of n. But these things here, each of these two terms are strange non-integer terms. It's just when you add the two terms together or subtract them, you'll always get an integer. So when n equals 0, it's not too difficult to just write down, and you'll see why f naught is 1. That works out. Even when n equals 1, it's a bit messy, but you could compute that, and you'll get f1 equals 1. It has to, because we picked the coefficients to force that to happen. But if you pick n equals 17, for example, and take 1 over root 5 times phi to the 18th minus 1 over root 5 times this number, which actually is just 1 over phi, minus 1 over phi, to the 18th power, why in the world should that end up being an integer? If you expand everything, you'll get all these things that involve integers and integers times root 5 in the numerator, and then what will happen is all the parts that don't involve the root 5 will cancel from the left and right. You'll end up with stuff that involves root 5s, and that will cancel these root 5s on the bottom, and you'll end up getting an integer. But that's not at all obvious until you work out some examples, and of course, you know that this formula came from the fact that we were finding a formula for an integer sequence. How fast do the Fibonacci numbers grow? What does this look like when n is really big? When n is big, I claim that f sub n is really just about 1 over root 5 times phi to the n plus 1. the Fibonacci numbers grow just like powers of the golden ratio. Why? Because when n is big, this term on the right gets really, really, really close to 0. 1 minus root 5 is about negative 1.2 divided by 2. Divided by 2 is like negative 0.6. And when you take a number like negative 0.6 and raise it to a big power, it tends to 0 very quickly. So in fact, one way to think about the Fibonacci number is to look at this number, 1 over root 5 times the golden ratio phi to the n plus first power, and that will be close to an integer, the difference being this thing, which gets vanishingly small. And just ask what integer is this thing closest to, and that will be the nth Fibonacci number. Another way to look at that is that this formula tells you immediately that the limit as n goes to infinity of fn plus 1 over fn will be exactly this golden ratio phi, because they're approximately the size of powers 1 over root 5 times powers of phi. So each Fibonacci number, and let me go back here, where we wrote down the Fibonacci numbers. When you get to really big Fibonacci numbers, each one is approximately phi, the golden ratio, which is about 1.6, times the previous one. That's certainly not obvious right at the beginning, but even here you're multiplying by something that's approximately this golden ratio, and you can see it more as you compute more and more terms.